So we need a particle factory that initializes particles. We're just going to call it init particle and the index. And we'll need a randomizer, probably in a wide variety of classes for different reasons. Let's go into game 1, and after positions, before render targets, on the top of game 1, we'll add a section called utilities, and we want this to be available everywhere, so it's static. Random RND. We'll need to be using system, so that's resolved. We still need to initialize our randomizer, so go into initialize, and right before input, we'll put RND equals new random, and we'll say init utils. If we get any other utilities, we'll just add them here and put the heading up here. So for variation, we're going to create a couple of random variables, and they'll have to be cast to float. So we'll say game1.rnd next 2 minus 1. So that'll get a random number between -1 and +1. Another floating point, same thing. We can just copy this. We're creating a new particle, so let's say particle P is equal to particles I. That's the one we want to work on. The particle's already created. We're just setting a new one by initializing it to new values. So we'll say its color is the start color. Position is at the emitter. We could randomize the position in the X and Y directions, but we're not going to. Say scale is start scale times float. We'll randomize the starting scale a bit so it's not all the same. Next double plus 0.5. So 0 to 1.5, or wait, no, 0.5 to 1.5. Yeah, because you don't want it anywhere under 0.5 because it'll be way too small. Velocity.x is velocity range times randomizer 1. And we use a different randomizer, velocity in the y direction. So same sort of idea, times R2. We're going to add to our velocity, initially, a spray direction. So it kind of has a bias motion in a certain direction. Say the rotation velocity is going to start off at rotation speed times R2, so it's got a little bit of variety. So each particle is rotating at a slightly different velocity. And we'll set the initial rotation so they aren't starting in the same orientation, because that might look strange, times 10. And this is randomized, so setting the rotation to be that number times 10 is going to be fairly random. Rotation offset, p.life is going to be the lifespan, because that's what we want it to start off as, and it'll slowly decrease over time. When it reaches 0, we know the life of that particle is done. And so we're going to set that value to be somewhere, not next double, we want an integer, so next, somewhere between minimum life and maximum life. Another way you could do that too is just have it so that when it scales down to a certain size, or the alpha fades to a certain amount, depending on how you're doing it, then you can have it trigger that that life has become 0, or that the particle's dead or whatever, and it has to regenerate a new one. Like I was saying, if for example we wanted to spread the fire out, we could add a random amount to the X value where it starts based on the emitter width, but we're not going to do that for this one because we don't have any particles that need that. We can even have it set so that if emitter width is greater than 0, then it actually does that. So I'll leave that up to you. Next we need to build our updater that updates all the particles. Boolean is projectile, and in our case we are dealing with projectiles. So is projectiles mostly used to deal with whether or not we should be moving the particle system and slowing it down by some dampening of value. If dead, I'm just going to return. So our projectiles can actually die. A regular particle system just kind of keeps going until you tell it to turn off. So you may need to program this in different ways depending on how you want it to work. Emission world position, we're going to add in the emitter velocity. The particle effect system is going to be moving based on emit velocity, and emit velocity is going to slow down depending on the dampening value. So if you don't want it to slow down too fast, you'd put it at 0.99999. If you want to slow down very, very, very fast, maybe something like 0.2, because then it would only be 20% of its velocity in the previous frame, so that would be instantaneous virtually. Also, if our emitter is traveling really slow, we don't want it to stick around too long, so we'll say if it's less than 0.2, .x, and emit velocity.y less than 0.2. Same thing if it's greater than 0.2f. It's got to be between those two values. That's what I'm saying, and for all of this. Negative 0.2. Did I put positive here? Yes, I did. Negative 0.2 greater than negative 0.2f. In the y direction. If all of those situations are true, then we know it's between negative 0.2 and positive 0.2 in both the x and y direction. We'll say spawn is false. So we don't want this particle system to make any particles. We want it to start fading out. and then when it runs out of particles, it is considered dead and becomes removed. So the first thing is we need particles to exist in the first place. If our count is less than capacity, then we're allowed to add particles. And if we can spawn, then we're also allowed to add particles. If those two cases aren't true, then we can't. So we can in this case. So we'll say init particle, we'll pass in count, which is the current index where we want to add a particle. And then we'll increase that index. Instead of going do while, say while first, because we might not have anything to loop through. Integer I is 0. So if I is less than count, we'll do whatever's seen in these brackets. We don't want infinite loops, so immediately when I create one of these, I make sure that we increment our counter. Instead of going particles I.life minus minus, let's just go like this. This is going to save us a lot of time. It's less to look at. We'll just say particle P, and P will represent the current particle that we want to deal with. I'm going to say P life minus minus. So the life is counting down. We already know that if P.life is less than or equal to 0, then we need to reset that particle. That is, if we're allowed to. So if spawn, we can init particle at I, index I. Otherwise, if the alpha, the color, is greater than 8, so if it's greater than some really small number, we'll count down the alpha. This just speeds up how fast the particle fades, because we know the life is really small. We can no longer spawn anything, so we need that particle to fade out fairly quickly. And because we don't care about this particle anymore because its life is less than or equal to 0, we'll just increment the counter and say continue. And that jumps back to here. If we don't increment the counter before continue, we're going to have problems. And here we can say the velocity in the y direction is going to be influenced by gravity. And we'll say that its position in general is influenced by its velocity. And its rotation, obviously, by its rotation velocity. So a lot of this you might be thinking, well, that could be inside the particle class itself. And like I said, just to maximize performance, this should be, in theory, a little bit faster. Scale rate. And then this is going to be unique to the Fire particle, so that's why I have this switch in here. Particle type. So sometimes there's certain things that only certain particles will do, and that's where you put in these unique behaviors in your switch. If the color green greater than 2, then we're going to reduce that color, and we'll just copy that. Same with blue. Blue is big enough that it's okay to reduce. Same with the alpha value. And for fire, we're just going to leave red alone. So red does not change. And this way, if it's like a white color, it'll fade from a white to a yellow. Depending on how you set up your green and blue initially. You'd want your green to be higher, blue to be smaller. And then it would go from that yellow to sort of an orange and then to a red. And the red would slowly darken if you had the red count down a bit too. But we're not going to do that. We're just going to fade out the alpha. Scale is less than 0.02f. And we'll just keep the scale where it is. We don't want it to shrink into nothing. We're also going to need to keep track of how many of these particles have life less than 0. So we'll go here and say comma c equals 0. And then in here, before we say continue, we can say C++ to count how many of these are dead, basically. And when they're all dead, or when they all have no life, then this entire particle system should be dead. So let's go down here after the while, after we've looped, and we'll see how many we added up during that loop. If the number that don't have life is greater than or equal to count, and we'll say dead is true. No particles have life. Particle system is dead. And to draw these should be fairly easy, actually. We'll take an offset value that we're allowed to pass in to offset the position if we want to. Not entirely necessary, not in this case. And for int I equals 0, I is less than the count, we'll say p is equal to particles, and then that way we don't have to keep saying particles I. Say pause for position, convert world to screen p.position. So particle position is in screen coordinates now, and you might want to just inline this actually with something simpler. It's more code to look at, but it would probably be a tiny bit faster. If you got a lot of particles, it might make a difference. P position plus offset using the source rec, particle color, particle rotation, where it's going to rotate around, scale, And that should do it for drawing it. Just going to pause it, format that a bit. There may be situations where we may need to do this with the quad batch. We don't really want to switch back and forth between sprite batch and quad batch too much if we don't have to. So let's make it so we can do the exact same thing with quad batch, which is practically the same code. We can copy this. And the difference is with quad batch, the texture is actually set in the begin. It's assuming that you're using a sprite sheet, trying to minimize texture switching and not having to sort. So we'll say plus offset in here, just doing it there rather than here. You don't have to do that. And I'm going to say, so all I'm really adding in here is minus center times p.scale. So that stuff's not internal to quad batch because I didn't want that as default behavior. So then here we can just say pause. Oh, I noticed a bug in the sprite batch version because right here this is still in the world coordinate. So let's just change all of this to pause, POZ, and add offset in here. That should do it. There. Now, this should work. Yes, it will work. I just went over here and changed quad batch to use a capital B like sprite batch does, and set it to do that for all references to quad batch, just for consistency. We'll go back into our player class and go down under the Meow Motion Animation stuff, that section for spells and effects, and we can add a list. So this is a bunch of particle systems. So we can have a whole bunch of fireballs shot off at once, a whole bunch of different particle systems. Oh, and I don't want to have to use using. So let's go into particle effects here, click on system, go to the top, let's just change this to just platformer. Go back to player, and we'll type in spells. That'll be the magic balls, or magic fireballs. We'll go down to load, just sort of doubling as our secondary init. And at the bottom, we'll put spells equals new list particle system. And then that should create a new list, particle systems. Alright, then we'll go into attack, and for spell parameters, we'll set for this particular attack, the spell velocity is going to be -6, 0. And that would be if he's facing left. If he's facing right, though, direction, we don't want to use this facing thing because the direction he's traveling and the direction he's facing might not always be the same. Spell velocity dot x is equal to 6. So we'll just switch it to positive value if he's facing right. And we'll start a spell as a new particle system, and then we can add it to our list after. So we'll say new particle system, starting at the position of the character, and we'll also add in 2 times the character's velocity, so it's offset partly for compensating for the character's motion. That way the spell isn't starting partly inside the character as they're moving quickly. And we'll use the spell velocity we just made. We'll also add in part of the character's velocity too. Oops, spell velocity dot x divided by 2. Just a horizontal direction. We'll say max particles will be 90. That's how many we'll allow. 90 should be fine. We want to use fire, and we'll want to use the texture for the tiles image that we passed in to player. And we'll set spell emit velocity dampen. For this spell, we want it to slow down fairly slowly. So it's got sort of half decent range. So 0.99, so it'll be 99% of its previous velocity every cycle. And then we'll add this spell to our list. So in the future, you may want to have it so that your hero attack passes in a parameter for the type of spell and does switches in here, or just has a different state for different types of spells depending on how drastically different it would behave. Now in player update, we'll go down near the bottom and we'll make sure we update those spells. Otherwise they're not going to do much, just going to sit around. While I is less than spells.count, we'll update each of those fireball spells, setting is projectile is true. If a spell system or particle effect system is dead, then we'll remove it, not remove all, remove at I, and make sure to do I++, or we're going to have problems. There. So let's go to our player draw and go to the bottom of that where we show our spells. We'll end the player drawing and start a batch, passing in the texture, and we're going to be using additive blending for this, so make sure to switch to additive. And use linear clamp, then solid state will be none. Okay, so we'll say int I equals 0. While there's any spells existing, I++, and then we'll just draw. We don't need an offset, so we'll set that to 0, and we'll give it access to quad batch. Oh, this should be .begin. There, now it understands.